Okay students, last time we have seen fixed size partition. Even if we go for different size partition, we used to face some problem with the leftover memory. The number of active processes is limited by the operating system. That is, the operating system limits the number of active processes by predetermining the number of partitions. Only those many processes will be included as many partitions you have. If we go for a large number of very small processes, then also the memory space will not be utilized efficiently in either of the case, whether it be a fixed or variable length partition method. Then the solution we can opt here is dynamic partition. Now see what happens in dynamic partition. The partitions are done according to the process size. So this varies in length and number. Here, the process is allocated a memory space as much as memory is needed by the process. Let us have a look at an example. Suppose we have a memory. Right now we haven't done any partition to the memory. Only some of the space is reserved for operating system. Rest of the memory is free. Now there comes 3 processes of variable sizes. So we did memory allocation according to their sizes. As you can see in the figure, P1 is of 20M, P2 is of 14M, P3 is of 18M, and then we have a leftover space of 4M, which is free for the next partition. Now assume that P2 have executed completely, and now the space occupied by P2 is freed up. And then there comes another process P4 whose size is less than that of P2. But still the size, it is compared with the available free size here in the memory. It is 4M and the size of P4 is 8M. So P4 can't be placed in this free area of memory. So next free area was the space occupied by P2. Still now P2 has executed completely. Now the space is available. So P4 is allocated this space. Now what happened here? Since P4 is having less size than P2, it occupies an area which is required by P4, that is 8M. And then we have again leftover space in between. That is 6M is again 50. Now again P1 has executed its execution, and then there comes another time we need to load here P2 again. Now see here what is happening here. We are allocating processes as much space as they require, but since the last partition is of greater size, we are facing here a problem of fragmentation. Now this is happening. This is not internal fragmentation because the space allocated to the process is the same as it is required by the process. So here comes the term called as external fragmentation. Your memory external to all processes is fragmented. Now this problem of external fragmentation can be resolved by compaction. In compaction, operating system moves processes so that they are contiguous. Now obviously this is time consuming, and again it wastes some of the CPU cycles, but still the leftover free area is again here combined together to form a large area of free space. Let us see how this can be done. Now operating system must decide which free block to allocate a process. Here the operating system decides which of the free block should be allocated to a process. And how it will decide? There we have mechanisms. First is best fit algorithm. In this algorithm, the OS chooses the block that is closest in size to the request. Request here means closest in size to the requesting process. But this algorithm is considered as the worst performer, since smallest block is found for process and the smallest amount of fragmentation is left. See what is happening here? We are calling it as a best fit algorithm because the strategy here it applies is it will choose a block whose size is closest to that of the requesting process size. It is considered as worst performer because here if you find the smallest block that is suitable for the requesting process, then you will face the smallest amount of fragmentation. The fragmentation that will be caused will be very less size. And there again you need to run memory compaction oftenly. Very frequently you have to carry out memory compaction. Next algorithm is first fit algorithm. It scans memory from the beginning and chooses the first available block that is large enough. So this criteria is placed by scanning right from the beginning of the memory to find the first free block that is large enough to satisfy the requesting process. This is the fastest algorithm and it have many processes loaded in the front end of the memory that must be searched over when trying to find a free block. See, an overhead we are facing here, though it is considered as the fast algorithm, but unnecessarily we are searching a lot of memory area in the front because the first free block will be found at the beginning. Then you have to keep on searching right from the beginning and then find the first free block in order to allocate it to the requesting process. Next algorithm is next fit. Here the strategy is to scan memory from the location of the last placement, and I think it is quite efficient algorithm because we are not wasting our time in searching from the beginning of the memory to find the suitable block of memory for the requesting process. So we will scan right from the last placement. That means lastly what was the process that have been allocated memory at the last time. Start searching from there. Now it is considered as most often allocate a block of memory at the end of memory where the largest block is found. See, the result of compaction is you will find free area at the end of the memory, and here it will like in compaction all of the allocated process will be shifted, will be compacted, and a free area of memory will be at the end of the memory. So here you will find the largest block of memory. So it will allocate the process from this available block of free memory and is broken up into smaller blocks for allocation. Now compaction is required to obtain a large block at the end of the memory again. Now here we have a figure showing all of these three algorithms. Look at the figure A here. This is before allocation. We have these some of the area is reserved for operating system. Then here some of this shaded part indicates that we have allocated processes over here, and this white portion indicates free block of memory before implementing any of the strategies here. Now figure B shows you what happens if you go for first fit. See here, there is a request for a process, there is a request from the process for memory allocation. So it will find the first free block. See here we have 22M. Before allocation we have the scenario. This is first free area. Okay. That is quite enough for the requesting process. So first fit will do will select this particular portion for allocation. What is happening here? 6m is left over. Again, it results in external fragmentation. Now, in case of best fit, it will find the suitable block. See, it will find the suitable block here. So this 18m is suitable for the requesting process because its size is 16m. So here we have again the small compaction area, small fragmentation area that is left over, and it can't be allocated to any of the process because it is so small, and this happens with best fit algorithm. The next fit algorithm chooses from this larger area of memory which is free, which is available for allocation. It will select a portion and do partition from this available portion. I hope you have understood this concept. Now we'll move on to the next point, that is buddy system. Now here the entire space that is available is treated as a single block of 2 raised to u. Here we are treating the free space in relation to 2 raised to u, 2 to the power u. If a request of size s where 2 to the power u minus 1 is less than s and s is less than equal to 2 raised to u, entire block is allocated. Now let us understand what do we mean by this. Since we have a available free area which is treated as 2 to the power u, if a request from some process is there whose size is s, now here we need to check the condition whether the size of u is within this limit 2 raised to u. If so, then see, within this limit 2 raised to u minus 1 and 2 raised to u, the entire block of memory is allocated here. Otherwise, the block of memory is broken down into 2 equal parts, and we call these 2 equal parts as buddies. And this process continues until smallest block which is greater than or equal to s is generated here. What we are doing, we are just checking the size of requesting process. If it is within the condition, then the entire free block is allocated to that requesting process. If not, then we will divide the available free space into equal parts, and we are calling these 2 equal parts as buddies. And we will continue to do this splitting until a block which is greater than or equal to the requesting process size is generated. Now here we have an example to better understand what do we mean by buddy system. Look here, we have 1 megabyte of block which is free for us. Now there comes a request of 100k. A process is requesting 100k. Since 1 megabyte is there, so 100k this is quite smaller. So we will partition this 1m of memory, 1 megabyte of memory, into 2 equal parts. And 2 equal parts here formed as 512k and 512k. The request is 100k. Still we can go for a further splitting. Okay, and this further splitting is here done. See here, a request, a process of size 128k occupies a space here from this half part, which is again divided into 256k. Then for 256k is again divided into 2 portions, 2 equal portions, 128k, 128k. And process A occupies 128k. Since the request is 100k, but still it cannot be further divided because here we will, if we further split this, we'll be getting only less than 100k of free block. So we will use this. Okay, then there comes a request for 240k. Now we'll search for an available partition. If we do not find this, then we further split the partition. So see here, the suitable, which is greater or equal to 240, is here we find 256K block. So this will be assigned to process B. Then there comes a request for 64K for process C. Now here we have 128K, which if we split, we get two equal parts as of size 64K. So we will do this, and here we have done the allocation for 64K. Now again there is a request for 256K. Now the remaining portion is your free block. So we'll split it again, and this process continues here. Then if we release it, if we release B, it is available again for the next process. If we release A, then this is available as it is. Now if there comes a request of 75K, here it will be given for the process E, but the size of block we are allocating is quite greater than 75K. But we cannot find another suitable free block, so we can utilize this. When we release C, again this is combined together, 64 and 64 again combined together, and we have 128K of free block available for us. If we release E, process E is released, then again this forms a bigger portion of memory area here. All is combined together. Okay. I hope you have understood this. Now this tree representation of buddy system is shown here. The same thing is shown in terms of tree representation. See here, one block, free block, is divided into two parts of 512. Now this 512 is again divided into two parts of 256K. Now 256K is further divided into two parts, equal parts, 128K. If we further split 128K, we'll get 64K free blocks available for us. Now the next topic is relocation. Now when a program is loaded into memory, the actual absolute memory locations are determined here. When we load the program into the memory, then only we can determine its absolute address. Now a process may occupy different partitions, which means different absolute memory locations during execution. See, when a process is brought up into the memory, it occupies a memory space, which we call it as the absolute memory address. Now next time if we do swapping, if we remove, there are many situations where we need to swap the process in and out of the memory. When we take out the process out of the memory, then then it frees up the memory area which has been occupied by that process. Now when there comes a new process, maybe the same area is utilized for the new process. And next time when we feel like reloading the earlier process that we have swapped out, then it will occupy a different location. So here, this is a concept of relocation. This is done during swapping also, as well as in compaction. Now relocation has a relation with addresses. Now, there are three kinds of addresses: logical address, relative address, physical, or which is also called as absolute address. By logical address, a reference to a memory location independent of the current assignment of data to memory. Here logical address is an address that is actually a reference to a memory location which is independent of the current assignment of data to memory. It is independent of the assignment of data to memory here. Whereas relative address is an address that is expressed as the location relative to some known point. Like we know some location here, and using that location we are trying to relate it to the current location. Okay, forming a relation with the known point. Absolute address is the actual location in the main memory. So here we have three type of addresses. Logical address, which is independent of the current assignment. Okay, it is only a reference to memory location. Okay, independent of any of the assignment that is done currently. Relative address is an address that is expressed in some relation to a known point in the memory. An absolute address is the actual location occupied in the main memory. Let us understand this with the help of this diagram. See, here we have a base register. This is actually the main memory. Here we have a process into the main memory. Okay. Now a process has your process control block. Then the instructions are written within this program area. The data associated with this process is stored in this data area. And here we have a stack for frequent operations of loading and removing certain sort of data. Now here we have a base register. Look at this, how a relative address is formed. A relative address is formed with the help of an adder. A base register is added here. The content of the base register is added to the adder, which forms an absolute address to the memory location. Okay. So base register is the starting point of your process. From the that means the process from where it begins in the memory, that's the starting location. Now here we have bound register. In case of an interrupt to operating system, bound register here defines the ending address of the main memory or ending address of the process. So base register will define the starting location and bound register will define the end point of the process. Now here during execution, these registers, what do they indicate? Base register is indicating the starting address for the process. Bound register is indicating the ending location of the process. Now these two values are set when the process is loaded or when the process is swapped in. These values are loaded as soon as you load a process into the memory or as soon as you take out the process from the memory. Now the value of base register is added to relative address to produce an absolute address. As I said, that base register content is added to the relative address in order to form absolute address. The resulting address is then compared to the value in the bound register. See, by the addition of these two values, that is base register value and relative address, whatever the resultant value is formed, that is compared to the value in bound register to make sure that it does not cross the ending location of the process. If the address is not within the bound, an interrupt is generated to the operating system. See, if the resultant address is within the bound, then it will show you the relative address. Right? It will point out to the address in the memory, right? But if it crosses the value in the bound register, then an interrupt is generated to the operating system. Now the next point here is paging. Now the concept of paging is to partition memory into small equal fixed size chunks and divide each process into the same size chunk. Now here what we are doing, we are partitioning the memory into small fixed size area, we are calling it as chunks, and even we are dividing the processes as well into the same size chunks. That means here the memory that we are dividing should be of same size as the size of the process that is divided into chunks. Now the chunks of processes are called as pages. We are dividing the processes into small parts, small chunks, and we call it as pages. We are dividing the memory into small parts, we are calling it as frames. Operating system maintains a page table for each process. As the processes are getting divided into pages, the operating system needs to keep a track of all of the pages of a process, and for doing so it is maintaining a page table for each process. Now here a page table contains the frame location for each page in the process, and memory address consists of page number and offset within the page. Now just try to understand what is the content in page table. Page table contains the frame location. Remember, frame we are calling for memory that we are dividing into smaller chunks. Okay, so if this page is occupying some of the frame, then it is maintained in the page table. The entry for the same frame is maintained in page table, and even the memory address of the page number and offset within the page. So memory address consists of page number and an offset within that page. Now here we have processes and frames to better understand how it works. See here we have divided the memory into number of frames, 0 to 13 you can see. Now here we have a process called as A. The name of the process is A, and we have divided this process into pages. So process A is having 4 pages labeled as A0, A1, A2, A3. Then we have another process that is B, and we have divided it into 3 pages, equal size pages. So maybe process B is smaller than that of A, so it is having less number of pages. Then we have process C here, again having 4 number of pages. Now we have finished with the execution of process B. Now these 3 frames are free for allocation, and there comes another process called as D, which is divided into 4 pages. So see here, 3 pages are occupied here just after the process A, and last page is having some different location. So this happens in paging. And then you have process D, another page. Now here is the figure showing you the content of page table. As we have discussed here that we in this example we have 4 processes: process A, process B, process C, and process D. So here each process is having a page table, and look at the entries for each individual process. See, process A page table is just giving you the location of the frames that were occupied, that were allocated to process A, all of the pages. Then for process B, since process B have finished with its execution, so there no memory frames is allocated to process B. Look at process C, it is occupying frame number 7, 8, 9 and 10. And process D again 4, 5, 6, 11 and 12. And there we have free frame list for just checking out whether there is free frames available for the next process. To keep track of free frames, we have another list called as free frame list. Now the next point here is segmentation. In segmentation, we can divide a program into segments. Now segments may vary in length. Like paging, we divided the program into equal size chunks, that is called as page. Here we can implement a segmentation and we can divide the program into segments. Now there is no such condition on segments that it should be of same size. The segments may vary in length. There is a maximum segment length again. Now here addressing consists of two parts, a segment number and an offset number. Like in paging, we used to have page number and an offset. So here in segmentation, we have segment number and an offset. It is similar to dynamic partition. We can say that segmentation is very much similar to dynamic partition. Let us understand with the help of this example. Look at the figure carefully. Here we have a relative address of 1502 which is represented in binary form as the sequence of zeros and one as written here. Now this happens in partitioning. The user process, whose size is 2700 bytes, occupies this area. Okay. Now in case of paging, this was in case of partitioning. The same scenario if we look for in paging, then we will divide this process into 3 equal size pages. Okay. And then the address is formed with the help of page number and an offset here. So page number is 00001 and then offset is 478, whose binary conversion is shown here. But this results in internal fragmentation. If we go for segmentation, then see logical address is formed using the segment number and an offset here. Now see, we have a condition. We do not have any condition over segmentation. The size of segments may vary in length, which we cannot do in paging. And hence we faced a problem of internal fragmentation. But see here in segmentation, we will not face any fragmentation problem, as the segment may have different sizes. So here we have the process is divided into two segments. Segment 1 size is 1950 byte and segment 2 size is 750 bytes. I hope you have understood this concept. That's it for today. Next point we will discuss in the next lecture.